everyone, welcome back you all on another video on DSP processor. In this video, we are going to cover the math accelerators, that is very important tools to enhance the computational performance on F2837xD microcontroller units. So why this is most important when you are a control engineering and you are designing a control task to drive the inverter, motor or any power electronics applications and smart grid technology, robotics. Okay, because in all these technology you have to perform several parallel tasks and that should be as fast as possible. Okay, so in that case what you can do, you have to go for the parallel processings or you have to use some fast processing things, your math operations and your the computations and your processing should be as fast as possible. So in this case, the C2000 family of the microcontroller addresses these challenges with the array of integrated on-chip hardware, math enhancement, and with the math enhancement it will dramatically enhance the performance of the microcontroller units in many real-time applications. So we will see with this enhancement and without this enhancement how much performance is improved in the subsequent slides of this lecture. Okay, so what enhancement they have made to improve the performance of the system? So that will be math enhancement they have made, and these enhancements are the control law accelerators, floating point units, trigonometric math functions, fast integer divisions, and Viterbi and complex math units. So as you can see here, this is the system block diagram with the math enhancements capability. So here you can see, here the CPU is the 32-bit floating points fixed point central processing units, and it is also having its own capability to provide the computations. Other than that, it is having the floating point math units, and this floating point math units will be integrated with the CPU to do the floating point activities. Further, there will be trigonometric math functions to do the trigonometric operations like sine theta, cos theta, and that is required for alpha beta to DQ domain and alpha beta to DQ domains, and any other math activities whatever you are doing. There will be fast divisions to divide the a or ax divided by y or a divided by b. You can do the fast integer divisions, and there will be Viterbi and complex math CRC units, and that units will be adds hardware support for communications, complex math and CRC calculations. Okay, so a 32-bit CPU, it's provides 32-bit processing capability. As we have discussed, floating point math units is seamless integration of floating point hardware into the CPU, and CLA and okay, so here CLA is a floating point CPU operating at full speed of the device, and this is the independent of your CPU, and this will be operating at the full speed of the device, and it is designed to perform control law computations with minimum latency. There will be trigonometric math units that provide the hardware support for common trigonometric math functions, and fast integer divisions, and VCU, that is for hardware support for communication, complex math and CRC calculations. Okay, so first we will talk about the floating point units. So floating point, the format of the floating points are IEEE 754 single precision floating point format is used for the DSP processor. So what is the advantage if we are using floating point or a fixed point number? What will be the advantage in terms of cycle, in terms of computations? For example, if we are using the complex FFT, if we are doing the complex FFT, okay, and if there will be fixed cycle, right, and there will be floating point units, if you are using fixed point units and you will use floating point units, so to the FFT of 512 samples, if you are using fixed points, fixed cycles, there will be 63,192 cycles are required to do the complex FFT. And if you are using floating point units of the 512 samples, 512 points, you need 24,2433 cycles. So you can see here there will be drastically reductions when you are going to use the floating point units as compared to the fixed point units for the 512 samples. In the same way, if you are going to use for 1024 number of samples, and if you are using the fixed point cycle, you need this number of cycles. But when you are using the floating point units, you need 53,219 of cycles. So you can see it enhances the computation capability and enhance the performance of the system when you are going to use the floating point units, and you will achieve the results within these cycles. So it provides the fast computations of the complex FFT. For example, if we are using the square root, okay, and if you are using the fixed cycle, it requires a 64 cycles to do the square root of any number. But if you are going to use the floating point units, it is using a 22 cycles to do the square root of that number. So with the help of this example, you will understand how the floating point units is enhancing the system performance with 2 or 3 times faster capability. Now there will be control law accelerators. So what control law accelerators will do? So it provides and it enables the extremely high performance computations, and efficient processing is a critical for solving today's complex real-time control applications. Okay, real-time control system required a minimum latency, right? So whatever you are doing, you are performing a real-time activity, that should be as fast as possible, and there should be time delay, should be minimum, and there should be minimum time delay between the sampling, processing and outputting. Okay, so what is happening? Okay, you are taking the samples of your inputs and you are processing the data and you are getting some kind of output, right? So there should be minimum latency and minimum time period should be there to perform this task. So there should be minimum delay should be performing when you are doing the real-time applications, and there will be some time frame, and within this time frame all the computations should be happen, and you should use the input and you should get the outputs. So there should be fixed time frame. In that one, your processing, you should take the samples, your processing should be done, and your output you should get the output. Okay, so for example, you are reading the data from the ADC. Okay, so you are reading the data from the ADC, and the data in the ADC, and what data you are reading? You are reading the data, either voltage and the current. And in the controller accelerators, you are using the PID controller, and your output will be the PWM signals. Okay, so this is the task you have to do it. And the PID, it could be any other control algorithms, whatever you want to implement. So many advanced control system would be greatly benefited from an architecture that integrated these functions in such a way as to minimize latency and provide the absolute minimum samples to output delay. So that will be a great benefit. So whenever you are giving the inputs and you are getting the output with a minimum latency, that kind of architecture would be greatly benefit. So ideally this architecture would execute time critical control loop concurrently with the main CPU. So what CLA will do, CLA will perform all the activity with a parallel with the CPU, right? And in addition, the architecture must have a built-in protection mechanism to guard against overcurrent and overvoltage conditions. Therefore, the Texas Instrument implemented and they have developed the control law accelerators. Okay, so what is CLA, what it will do, how it works, what are the CLA benefits, and how can we use it? So as the CLA is a fully programmable independent 32-bit floating point hardware accelerator that is designed for math intensive computations. What it will do, it will boost the performance of the math function that is used in the program. So with the help of CLA, as it is running parallel, it is running concurrently with the CPU, it will boost the performance of your program. And how it works, it will execute the real-time control algorithm parallel with the CPU. And what is the benefit? When we are using the CLA, it managing low-level control loops with higher cycle performance improvement. And when you are using CLA, you can achieve performance improvement that is 1.3 times higher than when you are using the CPU. And for example, if you are using motor applications and any kind of solar PV integrations kind of thing, if you are using, you will able to enhance the performance of 1.3 times larger when you are using the CPU. Okay, so for example, if you are using CPU for the motor applications, CPU need 880 to 952 cycles to perform the task, whereas when you are using the CLA control accelerators, it will using 639 to 694 cycles to perform the same task. So it enhances the capability, performance capability by 1.3 times. So I recommend you, when you are developing the control algorithm for your any kind of applications, please use controller accelerators to improve the performance of the system. Okay, so there will be another benefit, as the CLA is completely software based. Okay, there is no hardware based things that you need to do. CLA is completely software based control, where in the coding, when you are writing the coding, when you are writing the program in the Code Composer Studio for the microcontroller units, the that 28379D, so you can modify in the code. When you are modifying the code, what will the benefit you will get? You are reducing the cost of the system to redesign the hardware based solutions. Okay, so it is software based, fully software based, so you can reduce the cost of the system to redesign the hardware based solutions. And what it can do, it can compute the FFT also, fast Fourier transform. And how can we use it in the program? That questions can come in your mind, like we are reading everything, but how can we use it? At the end we have to implement these things for the with the microcontroller units. Okay, but how can we use it in the microcontroller units? So just initialize the code, and whatever task you want to initialize, like for example, you want to do FFT, you want to do ABC to DQ transformations, anything, and it is just like a ISR. In ISR, what is happening, it is generating kind of interrupts, and it will go to the ISR. And what is happening in the ISR? In ISR, there will be one interrupt was generated, okay, and that interrupt will lead to leads to send in the ISR, and whatever code will be written, whatever task will be written in the ISR, that will be executed first, and it will come back to the main program. So it is the same kind of thing, but it is not interruptible, right? So it is like a ISR. So once it is started, it will be completed. It won't stop until it won't complete. And it does not use interrupt for hardware, nor it do any context switching. And one more thing, it eliminates jitter, and when it is eliminating jitter, it is therefore the execution time will become very less during that time. Okay, so now the trigonometric math units is also the same way as the floating point units. So, and it is the extension of the floating point units, and it enhances the instruction set of the floating point units. Okay, so TMU is the enhancement of the floating point units. Okay, so the TMU is IEEE 754 floating point math units, and that is also coupled with the CPU. Fine. And when it is coupled with the CPU and it is IEEE floating I754 floating point math units, the FPU provide a general purpose floating point math support, where the trigonometric math units focus on accelerating several specific trigonometric math operations. Okay, and the operations could be the sine, cosine, divide, and square root, and many more. Okay, so these are the basic operations that the trigonometric math units will perform. Okay, so it is the extension of floating point units, and that is enhancement of the instruction set of the C2008 and the floating point units, and it is efficiently executing trigonometric and arithmetic operations, and it is used in control system operations. Further, the floating point units provide a math support in the same way the trigonometric math function is used, and the example is sine, cosine, divide, square root, etc. Whereas it is also supported the multiplications, division, square root, sine, cosine, tan inverse, cos inverse, and logarithmic and exponent components. And how can we use it? At the end, the thing come in our mind, then everything is there, everything is available, but how can we use it? The simple thing, there will be library supported by that library is math.h library, and that is supported by all the mathematical operations used for the C2000 microprocessor. Okay, so what it can do? It can do the Park and inverse Park transform, space vector generation, DQ0 inverse DQ transformation, FFT magnitude, and phase calculations. So when you are using the CPU and when you are using the trigonometric units, so how the performance is improving? So when you are using trigonometric, when you are not using TMU, it is 85%. It is approximately 90 cycles it is taking. Okay, so but when you are using TMU, it is taking 12 and 13 cycles. So there will be 85% improvement by reducing the clock cycles. For example, if you are using floating point units 880 and we are using TMU, there will be 590 cycles is required to perform the same task as floating point units doing. So better to use the TMU while improving the performance of the system. Further, it is having the fast integer division, and the supported integer divisions are truncated, modulus, and Euclidean. And the data type will be 16, 16, 32, 16, 32, 32, 64, 32, 64, 64, and the format will be signed and unsigned. So this is the basic table, as you can see here. So when you are using CPU and a C operator you are using, like this operator you are using, and you are doing the 16 by 16 bit but divided by 16 bit, you're having the 52 cycles, number of execution cycle will be 52. But when you are using the fast integer division, it is having the 16 execution cycles. So improvement will be 3.3 times faster when you are using the fast integer division modules. Okay, the next is Viterbi and complex math and CRC units. So why VCU and what is it? So what is the VCU? A VCU is a tightly coupled fixed point units that improve performance of communication based applications by the factor of roughly 7 times, and it's reduce the cost by eliminating the use of separate processor, and generally it is used in a signal processing application, filtering and spectral analysis. And where we do the spectral analysis and why we need to do the spectral analysis. It is used to process motor vibrations noise to determine the impact of vibration on the system. Okay, if you are using motor and you are doing the spectral analysis of the motor, so we will get to know what is the impact of the vibrations on the motor and how the motor life can be estimated, and what can we do to improve the efficiency with the help of these analysis. So the most of the processing power in the microcontrollers are using the Viterbi decoding, FFT, complex filter and cyclic redundancy check. So what is the Viterbi decoding? It is used in the baseband communications applications, and it is having the 3 main part: branch metric calculations, 8 compare and baseband operations. Further, complex FFT and filters it is using the spectral communication and signal processing applications. So complex FFT and filters that are using in the spectral communications and signal processing applications. And what CRC will do? CRC, cyclic redundancy check algorithms, are used for verifying data integrity over large data block, communication packets and codes. Okay, so when you are implementing the code in C2028X and where you are implementing, you are using VC units. So how much the improvement will happen? As you can see here, there will be 25 times faster will be there when you are using the 16-bit CRC for block length of 10 cycles, 10 bytes, and when you are doing FFT, that will be 4 times faster, and when you are doing the complex multiplication, addition, subtractions, and when you are using VCU, that will be 10 times faster. Okay, so these things when improve the performance. So how can we program this thing? So with the help of TI2000 software, this is called Composer Studio. You can use the CCS Code Composer Studio to program all these things, and the supported library will be math.h, and you have to install the F2837xD block set, not block set. You have to install this library, everything, and you have to take care of installation of the software that support this board, Launchpad. Okay, so next video we will see the general purpose input output pins, and what are the how many GPIOs are there for the Launchpad which we are using, and how can we use for the different purpose. Okay, that we will see in the next slide, next presentations of this series. And if you haven't subscribed the channel, and if you have a comment, you can ask me in comment sections. And if you haven't subscribed the channel, please go and subscribe the channel for the latest update. Thank you very much.